Hi everyone, this is a really cool stage. I mean, it's like, thank you. It feels really amazing to speak in Poland and to speak in my city and like to even speak in my favorite movie theater. So thank you everyone for joining. And I will be talking to you about today about languages, about like how to work with languages, how they work under the hood. So. A few words about me. I work on open source at the Guild, mostly in the GraphQL ecosystem, and you can reach out to me or find me on Twitter as Aleksandra says. You can also check out my personal website, aleksandra.codes. The slides and some of the things I will be talking about will be on my website. So I wanted to talk also, like, what's the goal of this presentation? So this topic is something that may seem intimidating to developers, and like I wanted, like with this presentation, to maybe inspire you to start playing with languages or to play with like inner workings of languages. But even if you're not particularly interested in that, I still want you to take something out of it. So you may wonder, how do I benefit from this talk if I like build user interfaces or APIs on daily basis? So I want to give you a few examples of when this knowledge pays off. The first one is maybe you need a custom linter rule. Maybe you work in a code base that has a unique style and you want to enforce it. So writing a linter rule means that you have to work with abstract syntax trees, and you have to have some basic understanding of how the language works. Another use case, maybe you want to enhance your IDE. Maybe there's a boilerplate or like a coding pattern that you write very often, and you would like your editor to do this for you, to like replace something or to add code while you're typing. And this again means working from the language, working with the language from the inside out. It's very early for me. I'm not used to giving talks that early. Okay, another example. Maybe you need a custom domain-specific language. Like in some business domains, the rules can be very difficult, but they tend to be changed very often. So creating a DSL could allow business experts to modify them themselves. So some of those problems could be solved with a regex, but for some it's not possible. Like code is a structured data, it's not the easiest problem, so we need something more. And I wanted to give this talk, and because like I have some selfish reasons as well, because this is a topic that is very interesting to me. I have been working on tooling for the last few years, so this is something I needed to deal with on many occasions. But I also think that this topic can be quite a challenge, and that can be a fun area to explore. So first I want to talk to you about some theory, and I want to start with the grammars. So we have grammars in spoken languages. And like if we make a mistake in English or Polish or whatever other language, there's still a chance that people will be able to understand us. But if we make a mistake in a programming language, then like machine won't be able to deduce what we had in mind. So we have, like as everything in programming, like languages also have a spec. And this is what you see on the slide. It's like one of the most popular annotations for the grammar. You can see like, this is an example of a regular grammar. So something that is predictable. On the left-hand side, you see symbols, and then on the right-hand side, you can see the expressions that can be produced with the symbols. Here's a bit more complex one. We have context-free grammar, which is something that that we have to deal with in the context of programming languages. Context-free means that what comes next is not bound but by what was before. So like we can actually form like recursive grammars, and we can form like complex structures as we do with programming languages. And in other words, you can think of a regular grammar as like what comes next depends on the previous step, and you can think about context-free grammars as what comes next doesn't depend on the previous step. And the first one would actually be a good use case for a regex. But we're going to talk more about the second one today. And I also wanted to like briefly talk about like what are the different steps, like what's going on with the code once you write it. So let's say you wrote the code, like maybe in JavaScript, maybe in a different language. So what's next? Well, the first step that is common for like different paths of what can happen with the code is scanning and parsing. So firstly, there's a scanner step, and what the scanner does is it looks at your code like character by character, and it produces a stream of tokens. And for example, it can identify a const keyword or an equal token, and whatever else is allowed in the language you are currently using. And no, not yet. And then comes parser, and parser looks at this stream of tokens and tries to give context to it, like tries to, based on the rules that are in the language, it tries to analyze it and create this tree. You might have heard about parse tree or abstract syntax tree. Technically, there are some differences between those two, but I'm going to use those terms interchangeably today. So it may see that there was a const keyword, and later on there was an equal token, so it will deduce that it was a variable declaration, and it will know what are the children of that variable declaration node. And if we just stop there, and if we would want to just produce a result, we would have like a very simple interpreter. It's often called three-walk interpreter, and basically it means that it will go through this abstract syntax tree and calculate the result. But if we don't stop there, there will be an analysis part, and in there, it's sometimes called a binder. It goes through that tree, usually once, and tries to produce some metadata that will be used in later steps. So some examples are maybe it will keep track of environments, of the scopes, of particular variables. For example, in TypeScript, the binder step adds information about parent nodes to each node, so that then type checker can go like up the tree and down the tree very, very easily. And then we have an optimization part. So it usually means that the code, like by then, it will be in some intermediate form. It can be some kind of a tree, and it will go over like multiple rounds of optimizations, and each round is supposed to make like the next step easier. So one of the examples of an optimization can be like constant folding. For example, you have in your code like const x is equal 1 plus 2. So it doesn't make sense to calculate it in runtime. You can do it in the build time, and the compiler can calculate it to be free. And from there, we can go into another language. So we have transpilers. We can produce a bytecode, which will be then interpreted by a separate thing, or we can have a machine code that you can run directly on your computer. And one more piece of theory that I wanted to mention is that there's usually this misconception about interpreted and compiled languages. And it's very tempting to call a language like interpreted or compiled, but like when we saw that like the grammar notation, like nowhere there was any information about whether it was interpreted or a compiled language. So I wanted to tell you that it's not about like it's not like a language is compiled or interpreted. It's more about implementation. So we can have some implementations that are purely compilers, like we can have V8 Turbofan, Rust, GCC, or we can also have like purely interpreters, like Matt's Ruby interpreter. But in many cases, like many languages fall into this compiler and interpreter part. So we can have like Go, which has compiler and interpreter, C Python implementation of Python, or V8 Ignition. So basically, like the split is into three. So let's go one by one. So the first case is that like it's purely a compiler. So you write the code, then compiler comes, and it produces a machine executable that you can run on your computer. The next step, also we have a compiler that produces bytecode, and then you use interpreter to actually get the result. One example is V8 ignition, as I mentioned before. So we have like JavaScript code, and ignition compiler produces a bytecode, and then ignition interpreter actually produces us with a result. So this is what happens when you run JavaScript in V8 environments, so like Chromium browsers. And then the last case is when we have purely interpreters. So we write the code, and then there will be scanning, parsing, as we mentioned before, maybe some analysis, and then it will produce the result. It usually spends less time on the analysis part because there's no like back and forth with the optimization, but it also means that sometimes executing the code is slower. So now I want to show you some code. I hope that will work. It doesn't. Oh, I didn't touch my laptop. Yeah, that makes sense, a lot of sense. And now, yeah, it works. So for the purpose of this talk, I created a very simple programming language in JavaScript that I wanted to show you a few things based on that language. So let me go to my browser. Can you see it? I can make it slightly bigger. Okay, so this is the syntax of the language. It's very simple. It has functions. It has arithmetic operations, and you can see here how the lexer and parser and interpreter behave. This is a case of a very simple tree-walk interpreter. And so first, the lexer can identify different tokens. And then we can also see a parse tree with what the parser was able to come up with. And there's interpreter. I can also show you I have this evaluation steps, so you can see what was first. Make it. I hope it's still visible. Okay, so basically, the first step is it looks at this program as a whole. Then it goes to this function call. It tries to calculate what's inside, and then it produces the result. So I want to show you the code. There are tools that let you create new languages just from a grammar. Like you write grammar in the notation that I showed you before, and then it produces basically lexer and parser out of the box. But in this case, I used something called tsparsec. It's parser's combinator library by Microsoft. It's very minimal, and I used that because I wanted to show you something more low level. Okay, so what's going on? Firstly, I have different tokens, and the tsparsec part comes here. So I'm using this build lexer function, and I provided with information how it should treat different characters. So basically, I'm saying, for example, that well, if you see an equal token, please say that this is token kind equals, which is this. And this first argument means whether to skip it or not. In this case, equal token is important for me, but I don't particularly care about white spaces. And then the parser. In the parser step, I declare different rules. So, for example, this is, I think, the simplest one. So for a numeric literal, I'm setting this pattern that, hey, when you see a token kind number, please create this node with kind numeric literal with value that I'm also parsing. And I also have some metadata, but this is basically just so I'm able to do this highlighting in this application. Okay, and I still have some time, so I was thinking that I can add something to this language. And last time I did this talk, I added a print expression, and I was thinking that this time I will show you how to add support for arrays. So the first thing I have to do is to handle the syntax. Like I'm going to go with something like very simple that just has this kind of syntax. That is like very familiar to everyone. So right now I'm seeing an error that it can't like tokenize this input because like basically the selector doesn't know what's this square bracket. So I'm going to add a new token kind. Actually, I'm going to add two. Left square bracket. And thank you, Copilot. And right square bracket. By the way, if you're working with languages and those kind of things, Copilot is doing really, really well. And then I'm going to also create rules, how to handle it. And if I go to this application, then I see that right now it can handle the square brackets. But still, if I go to the parser, it doesn't know what this thing is. So I will. I have those helper types, so I'm going to create a new one, which will be an array expression. So I'm going to say array expression, yes, and I'm going to create a type for it somewhere. Let's say here. This basically lets me tell. It lets me express like what will be the shape of the node in the abstract syntax tree. So an array will have some elements, and the elements will be like different kinds of expressions. And I'm also going to add it to my expression union. Yes, and okay, that's not enough. That's only the types. So I actually need to go to my parser code and create a new rule. So I'm going to say const array expression. This is a new rule. Yes, something like this. And now I also have to like say how this parser should treat arrays. So I'm going to set a pattern on this array expression. Set pattern, yes. There's a function apply to actually apply a pattern. So, and what is array? This is some kind of a sequence. And in this sequence, the first thing will be a token, which is token kind left square bracket. Then we will have, it doesn't have to be that complex. So we have a list sequence. And in this list sequence, we will have an optional expression because an empty array is still an array, and it will be separated by a token kind comma. And we'll also close this array by providing this right square bracket to this sequence. And then, like the second parameter of this apply is something that produces the node. So we'll have kind array expression with elements that are of type expression and some metadata. This will actually be slightly different. I'm going to say elements of elements, yes, something like this. And I need to probably close this one. Okay, so now I also have to add this pattern to this expression. So this is an alternative. Like an expression can be print expression, function expression, variable declaration, assignment. I also need to say that an expression can be an array expression. And now if I did everything correctly, and if I go here and create an array, we can see an array expression here. We can also do a binary expression, and we'll see that the second parameter will be binary expression. I think we can also do a function call here. Sorry, a function, a lambda function. Yes, so we have numeric, literal, and a function expression. So the next thing to do would be to actually go to an interpreter and define how it should proceed when it is an array. And I was thinking that I can leave it as an exercise. So if you are, and if I can switch to my slides. Okay, 1 second. Oh, and one more thing, I call this language Olang because, well, shortcut for Aleksandra is Ola and Ola plus Olang. So I always wanted to create a language called that way, and now I have it. So here's the QR code. Feel free to reach out to me with any questions and contribute. I will be happy to help you with getting started to add more features to that language because, well, it doesn't have much right now. And yeah, thank you. You can scan this code. Will take you to my personal website where you can find my the slides from this presentation and some other resources. Thank you a lot.
Okay. Thanks for the talk. You questions. Can go, yeah, there's going to be questions.
Okay.
Let's take a seat,
okay.
Relax. We will wait for some questions from the audience. And I can kick you off with a question about, how do you get started with ASTs? If someone wants to, someone wants an easy starter, they want to try it out and see if they're going to like it, what's the lowest effort thing you can do to experience playing with ASTs?
Yeah, so basically, I assume that you mostly write in JavaScript. So you can go to website like AST Explorer or AST Viewer, I guess. Basically, if you Google AST Explorer or Viewer, it will take you to some kind of application where you can pass your code and it will display this abstract syntax tree. So you can basically see what's going on. You can see different nodes, the metadata that's there, and you will have a feeling of how many things there are. So that's one thing that is that could be a good start. And otherwise, I still assume you write JavaScript, so you can start playing with transformers. Maybe you would create a simple Babel transformer, or there's a library called JCodeShift that lets you write code modes or transformers that take your code, and you can, on this abstract syntax tree level, modify this code by changing some nodes or by, thank you, you noticed my, my voice, or, delete some of the nodes from the tree.
Okay, so if you want to start, the website is astexplorer.com?
Yeah, that's one of them. There's also Viewer.
Yeah, yeah, you can probably look it up in the search engine that I'm not going to name. Okay, so from the top questions, I'm not going to ask the top question because it's in Polish. Okay, so what is the overhead of this kind of language? Is it slower or similar to standard JavaScript, TypeScript, for example?
Well, so this interpreter is written in JavaScript, so it won't be the fastest language. But well, actually, this can be another exercise to rewrite it to Rust or maybe Go. So yeah, it's the fact that it's written in JavaScript. That's the first thing that makes it slower. And as I mentioned before, interpreters take more time to execute the code. Because they do it everything while walking the tree. So yeah, those are two reasons why, well, you probably won't use this language if you want to be performant, but it's enough to play with.
performance is a theme because the next question is also about performance. Do you have some tips on optimizing custom ESLint rules? Someone says they wrote their own, but it made linting really slow.
Okay, so there can be many reasons why it happens. Like possibly maybe you're walking like too many nodes. Maybe there are some like that there is a recursion, like you're going through that tree like back and forth. So I suppose well, one thing would be to just rewrite it and like go like slow, like split it into multiple steps and see where's the bottleneck. Because yeah, otherwise it's hard to say. Like basically, like you would need to like debug it and see when it does too much work.
Yeah, the thing is using a visitor pattern. So if you don't put a filter in front of everything, your code is going to run for absolutely everything that the parser was able to name.
Yeah, and that can be a lot of nodes in case of bigger projects.
Yeah, the sooner you filter out, the better. What else do we have here? Okay, this is funny. Why would you create your own language?
Well, for fun. Yeah, so basically I think like creating your own language or like playing with interpreters, transformers, code modes and so on, it gives you a better understanding of how the language you use works. So it may give you a better understanding of why JavaScript behaves the way it does, or like what are some like steps that each language has to take. So like in the long run, it can also help you write more performant code because you will have this like like you will have this idea of what can be going on underneath.
Thanks.
But mostly for fun.
Yeah, like don't we do everything for fun?
Yeah, exactly.
Okay, we have time for last one, and yeah, I think this one's going to be good. What are the coolest usages of this? Code modes helpful with migrating, etc. Like, I think this asks for your experience or opinion. What's the coolest thing you can do with ASTs? Yeah,
for me, mostly code modes. So, like, I don't know, it can help you migrate from, like, if there were possibly like many breaking changes in a library that you're using, it can help you migrate. Like ESLint rules, and I also a while ago I've been working on a framework, so we had a lot of that in the framework itself to like modify the code in the build time. And yeah, those domain specific languages, VS Code extensions, like you may want to modify the code. I know there's like one popular example is that when you write JSX and you want to modify the tag, then like there's an extension that lets you just change the left-hand side, and then the closing tag is changed automatically. So that's also something that is like I mean, you need to use ASTs to build something like that. Okay. Because it might be tough with Regex. Yeah. Possibly possible.
I really want to squeeze this last one in. So, any specific lessons learned about JavaScript coming from writing Olang? Great name, by the way.
Well, I think, well, I don't have any lessons about JavaScript itself. I have a lot of lessons about the ecosystem in JavaScript. Like when I was like researching some like modern tools that could help me write this language, I was a bit positively surprised with how many there are. Like firstly, that there are tools where you can just write a grammar and it produces parsers for you, and like there's like I use this TS parsec, it's really nice, but there are also other libraries that have like really nice API and that can lets you like move on like very, very fast with writing your own language.
Yeah. And people writing those parsers are really fun to talk to if you can understand them.
Yeah.
Okay, thank you for the talk. Another round of applause, please.